Welcome to a new session. Today we are going to study one application of Gauss's law. We know by using Gauss's law we can easily obtain the electric field for some simple symmetric charge configurations. Here in this video we are going to find electric field due to an infinitely long straight uniformly charged wire. Consider an infinitely long thin straight wire with a uniform linear charge density lambda. Since it is an axis of symmetry, the electric field must have the same magnitudes at these points. The direction of electric field is radial. We know if lambda is positive, that is greater than 0, then direction of electric field is outwards, and if lambda is less than 0, that is negative, then direction of electric field is inwards. Let us consider the charge of this infinitely long straight wire is positive, so that the direction of electric field is taken as outward. We know the electric field is everywhere radial in the plane cutting the wire normally, and we know magnitude of E depends only on radial distance r. So this is the radial distance. As r increases, the magnitude of electric field decreases. So radial distance r is the only factor that determines the magnitude of electric field. Now our aim here is to find the electric field at distance r due to this infinitely long straight uniformly charged wire. For that we are going to apply Gauss's law. To apply Gauss's law we need to consider a Gaussian surface. So here we are going to consider a cylindrical Gaussian surface with a radius r and length L, like this. So the length is L and radius is r. We know by Gauss's law the electric flux through a closed surface, that is closed integral E dot ds, is 1 by epsilon 0 times the charge inside that Gaussian surface. So for applying this we need to calculate the electric flux, that is the left hand side, and then equate it with the right hand side. That is the method we are going to do here. Here the electric field is radial. So the electric flux through the ends of this cylinder is 0, because the normal to this surface and the electric field are perpendicular to each other. That is, it makes 90 degree. So E dot ds at this end surfaces becomes 0. So electric flux through the two ends is equal to 0. At the cylindrical part of the surface, the electric field is normal at every point. We know it is same at every point because R is same for every point, and this magnitude of electric field depends only on the radial distance R. Therefore, electric flux through the curved cylindrical part of the surface is equal to surface integral E ds, because here the direction of the electric field and the outward normal to the small element ds on the curved cylindrical part of the surface are in the same direction. Therefore, we can write E dot ds is E ds, and we can write it as E into surface integral ds, because E is same for all the points on the curved cylindrical part of the surface. We know surface integral ds, that is the surface area of the curved cylindrical part of the surface, which is 2 pi RL if R is the radius of the cylinder and L is the length. Then this electric flux is equal to E into 2 pi RL. So we got electric flux through two ends of the cylinder is 0, and electric flux through the curved cylindrical part of the surface is equal to E into 2 pi RL. Therefore, the electric flux through this closed Gaussian surface, that is closed integral E dot ds, is only the electric flux through the curved cylindrical part of the surface, and we already calculated it as E into 2 pi RL. Now we can apply the Gauss's law, and according to Gauss's law, the electric flux through a closed surface is equal to 1 by epsilon 0 times the charge inside that surface. Here the charge inside the surface is the charge of the straight wire inside the cylindrical Gaussian surface. Here the charge inside the Gaussian surface is the charge of the straight wire inside the Gaussian surface, and we know it is the charge of length L of this straight wire inside the Gaussian surface. We know the linear charge density of the wire is taken as lambda, and the length inside the Gaussian surface is L. Therefore, the charge of the straight wire inside the Gaussian surface is lambda into L. Therefore, this equation can be written as 1 by epsilon 0 times lambda L. So, we got an equation E into 2 pi RL is equal to 1 by epsilon 0 times lambda L. L we can cut it off. Therefore, E, the magnitude of electric field, is equal to 1 by 2 pi epsilon 0 into lambda by R. You can also see this equation, that is the magnitude of electric field, is independent of L. Therefore, the magnitude of electric field at a distance r from an infinitely long straight uniformly charged wire is E is equal to 1 by 2 pi epsilon 0 lambda by R. We can represent it vectorially, then E is equal to 1 by 2 pi epsilon 0 lambda by R into n cap, where n cap is the radial unit vector in the plane normal to the wire passing through the point. And this equation easily shows that E is outward, that is, the direction of electric field is outward if lambda is positive, and direction of electric field is inward if lambda is negative. So, we found an equation for electric field at a distance r away from an infinitely long straight uniformly charged wire by using Gauss's law. Thank you for watching this video. Keep learning. If you are not yet subscribed to our channel, please subscribe it. Also, please like and share this video.